Hi everyone, today we're going to talk about the basics of thermodynamics. So some basic terms before we jump in. Heat is the transfer of energy by virtue of energy difference, and so the SI unit of heat is joules. And another important note to make is that heat always flows from high to low. So if you have a higher temperature and a lower temperature, heat will flow from the higher temperature to the lower temperature. Internal energy, that's the sum total of molecular kinetic energy and potential energy. And in theory, there is no highest temperature because you could just keep adding heat to a substance and it would still increase the temperature. Absolute zero, that's the temperature at which the molecules of a substance have their minimum kinetic energy. And theoretically, this cannot be achieved because the temperature as the pressure of a gas can never be reduced to zero. And finally, temperature is a measure of the average molecular kinetic energy in a substance. Note the difference here between heat and temperature. They are not the same thing. Heat is the transfer of energy, while temperature is the measure of the average molecular kinetic energy in a substance. Now let's jump into laws of thermodynamics. The first law of thermodynamics, otherwise known as the law of conservation of energy, is that energy cannot be created or destroyed in an isolated system. The second law of thermodynamics states that the entropy of any isolated system always increases. And so for our case in thermodynamics, the entropy of the universe is always increasing. The third law of thermodynamics is that the entropy of a system approaches a constant value as the temperature approaches absolute zero. And thermodynamics actually also has a Zeroth Law that they decided to add afterwards. And so the Zeroth Law of thermodynamics states that if two thermodynamic systems are each in thermal equilibrium with a third one, then they are in thermal equilibrium with each other. So what does this really mean? So let's say in the picture we have A, B, and C. If A and B are the same temperature and B and C are the same temperature, then we can assume that A and C must be the same temperature as well. And now we have three types of processes in thermodynamics. So we have an isothermal process. And so for this, we have a change of a system in which the temperature remains constant. So delta T equals zero. Isovolumetric process. This is a thermodynamic process during which the volume of the closed system undergoing such a process remains constant. So this would probably be a closed container in this case. And finally, we have adiabatic process, in which energy is transferred to the surroundings only as work. And so what this means is basically that in an adiabatic process, there is no transfer of heat throughout the entire process, because the changes that are occurring in the system happen so fast that there's no time for heat to be transferred. And so probably one of the most important equations you'll ever need to know in thermodynamics is Q equals mc delta T. So Q is the energy transferred or the heat transferred, so that's in joules. M is the mass of whatever it is that you have. It doesn't have to be water necessarily. Just in this picture, it states it as water, but it doesn't have to be. C is the specific heat capacity, so this will be unique for each substance. And delta T is the temperature change, so Kelvin or degrees Celsius. And just as a reminder, Kelvin, the freezing point for a Kelvin is 273, and then the boiling point for Kelvin is 373 Kelvin. And the freezing point for Celsius is 0 degrees, while the boiling is 100 degrees. And another interesting note to make is that Kelvin, we don't write degrees. So we only write degrees for Fahrenheit or Celsius, but never for Kelvin. And if you ever want to find the heat loss from an object, set the equation to heat gained equals heat loss. So negative mc delta T would be heat lost, and mc delta T would be heat gained. And PV graphs. So you'll see this a lot often in thermodynamics. So we first have isobaric. So pressure remains the same as volume increases. So that's the top left corner one. And then we have isochoric. Volume stays the same as pressure increases. So that is the top right. And we have isothermal, so temperature stays the same everywhere along the curve, so that is bottom left. And adiabatic, there is no transfer of heat throughout the entire process, and that would be bottom right. And so oftentimes when you're trying to read PV diagrams, you'll have to differentiate between adiabatic and isothermal graphs. So notice how an adiabatic curve is steeper than an isothermal curve. So if you ever have to differentiate on a quiz or a test, just remember that adiabatic is always steeper than an isothermal curve. And finally, finding the work done in a PV diagram. So this may seem complicated at first, but I promise you it really isn't. So when you want to find the work done in a process, it's the integral of the curve, so the area underneath the curve. So for example, for the picture on the right hand side, it's the area from the final state to the initial state, so the entire area underneath that curve would be the work done. And for a cycle, the work done is the area enclosed by the graphs. So in this case, you could think of it as a top curve minus bottom curve. So for the left hand side image, everything that's enclosed by the graph would be considered the work done in the process. So thank you for watching. If you have any questions, please make sure to leave them down below. I'll try to get to as many as I can, and see you in the next video.